Hello, everyone. Welcome to our talk, Distributed Machine Learning at Lyft. So in this talk, I will give a very quick introduction of how we define distributed machine learning inside our company. And then Anindo is going to focus on talking about some particular pains and our solutions to those problems. So machine learning is widely used in Lyft just like any other technical companies. And our decision making is majorly relying on machine learning models, different types of models, deep learning models, classical models, and even some other statistical models. And some examples are like price optimization, safety, ETAs, fraud detection, mapping, and incentives. So as a platform team, our mission is to build the machine learning platform that is scalable. So in order to build such a system, the first question we ask ourselves is, what are distributed machine learning scenarios? Feature engineering on petabyte level of data, building machine learning pipelines using the largest machines on AWS, using 1,000 GPUs to train a large model, or try 1 billion hyperparameter combinations to find the best? Well, they are all distributed machine learning scenarios, but we don't think they are the major cases. They are only the edge cases. What we want to focus on here are the practical scenarios that are most common in industry. We want to solve those problems for our real users. So first of all, let's take a look at the size of distributed machine learning. So we always talk about big data, but please don't forget there are also small data. And also, when you talk about data, please don't forget there are compute. We have small data, large data, small compute, and large compute. If you draw things in this matrix, it will give us a better picture of like what kind of problems we want to solve. Large data, small compute, which is the most common cases that almost every distributed computing framework is focusing on. You can see all kinds of benchmarks around those things. A typical example is you have like petabytes of data. You want to just group by some keys and get the mean, max, and average. So that's just a very simple reduce, and that can be fully parallelized. To be honest, there are many other things about distributed computing. So another scenario that people tend to ignore is small data, large compute, which is actually also very common. For example, the data scientists, they already created hundreds of tasks. And for each task, it will run like 2 hours. They used to use that, they used to run those using multi-process on a very big machine. And the question is, how can you utilize a distributed system and fully parallelize those 100 tasks on a distributed system? It sounds easy, it sounds straightforward, but actually, it's not straightforward on top of those popular distributed computing frameworks, such as Spark and Dask. Okay, with large data and large compute, we could have a scenario that have both. Like what I mentioned before, those edge cases, they're very, they are not very common. And there is another scenario that we tend to forget is small data, small compute. It's not cool, but it is still the very common case that every company has to handle. Right? So looking at this matrix, I'm not saying which scenario is more important. I'm just talking about we have these 4 different things we need to handle. So which size matter? So actually, we think all sizes matter. What we want to create is a unified solution that you can use the same approach to handle different scenarios. And another very important thing I want to point out is that actually, just by handling different sizes of data, size of compute, is not enough. An important thing we need to do is, as a platform, we need to encourage people to quickly reduce the size of data and the compute. So reducing the size matters more. We want to create the solutions so that to help people to quickly reduce the large data to small data, and large compute to small compute, so they can convert it to something that is within their comfort zone, so that they can develop, they can iterate. So I think that is even more important. So now let's look at the scope. For feature engineering and prototyping, of course, they will need distributed systems. For example, we need to pull the data from the database or from the feature store, and then normalize them, clean up them, and to provide the features. Also, when you prototype a machine learning model, you want to try different hyperparameters. And how can you run those parameter search in parallel in order to find the best combination? All these will need distributed systems. And it's like a typical batch system scenario. For model training, it's different. Model training, common scenario is the data is too large. The training data is too large to fit on one machine. Or the training is too slow on one machine. So that we want to consider using multiple machines, especially GPU machines, in parallel to speed up the process. And the model training, the distributed system, is a little bit different from the traditional batch system. For example, for deep learning training, we will need O-ring reduce. So the topology of the network will be different, but it is another type of distributed systems. For serving, of course, serving is a typical real-time distributed system. Both throughput and the latency are very important for us. For model monitoring or metric monitoring, it's a little bit complicated. So part of the monitoring should stay with the online service, should be integrated with the real-time system. And part of the monitoring, they have to be on the batch system. For example, if you want to detect the drift of your prediction, you will need to get your prediction. You will need to get your ground truth, right? And if the ground truth has delay, the availability of ground truth has delay, you will have to have a batch system to merge them together in order to detect the drift, right? So the point here is every step of the full machine learning cycle will need some sort of distributed computing. Distributed computing is valuable for every single component of machine learning. Okay, so here are our design principles for distributed machine learning platform. First of all, making big data small. So this is not only a technical design, this is also a mindset that we want our users to understand. Big data is not cool. What you need to do is try to make it small and then to think about the next step. If you have this mindset, actually, you probably don't need any fancy tools. You already can solve a lot of problems in a much easier way. Fast iteration, this is very important. We notice that our users could suffer from like slow iterations by just changing a parameter or just changing some part of the SQL, and they have to rerun everything. And it takes hours for just one iteration. This is just not practical for developing models or data pipelines. So we want to create those mechanisms for them to speed up the iterations. And we want isolated environments. We don't want people to have like a dependency hell. Like for example, someone is using TensorFlow 2, someone is using TensorFlow 1, and they just want to keep using their own environment. How can we keep them isolated? So using Docker image is the natural choice. And also using Kubernetes is the straightforward option. And another thing is layered cake approach. So one level of abstraction can never solve all the problems. It will either make things oversimplified or overcomplicated. So our approach is to have many layers of abstractions, layer on top of layers, so that different users and different use cases can choose different level of abstractions to use in order to minimize the unnecessary code. And another thing is time cost visibility. We must make people aware, we must make the company aware of how much time and how much money they spend on their machine learning projects. If for some like experimental machine learning projects, it costs like $10,000 or $20,000, it definitely doesn't make sense, right? So we want to make this visibility, we increase this visibility so that we bring attention to people that what they are doing. Is there any business justification for that? So actually, to be honest, I think time matters more to the users, but cost matters more to the company. Both are very important. Last but not the least, we want to make the system easy to use. So our design philosophy is for the common cases, like 90% of the common cases, they should be done by just one function call, nothing else. But we also have like a more complicated designs that can handle those 10% edge cases. But we do our best to simplify the cases that most people will use. We are not a believer of low code or no code, but we believe that we should always minimize the unnecessary code for any common jobs. So here is a high-level chart of Lyft distributed environment. As you can see, we are based on Kubernetes and Python. On top of that, we have three major parts, three major stacks. One is general distributed computing, distributed training, and distributed tuning. I'm not going into details about all these solutions. I just want to say that look at this chart. We use all kinds of different open source solutions. They have different design philosophies. They have different interfaces. And that is why it is very important for us to create a top-level API called the Lyft Distributed Libraries. This is to unify the usage and simplify the usage for the common cases. For example, I want to just distribute a task that I've already written locally, right? For example, I want to run a SQL on any type of data source, files, database, or anything else. Right? So we have this top-level Lyft distributed API so that people, for most people, they just need to interact with this library without knowing how to interact with the underlying libraries. But of course, it is transparent. So if you really want to use the lower level API, you have the full control. You can just use those open source libraries by yourself. And by doing this, we find that people tend to use our API as much as they can. And so that actually the code is much less and it's much easier to maintain the full stack of these open source projects. So now let me hand it over to Onindo, and he will talk about the pains and our solutions. Thank you.
Thank you, Han, for introducing the topic. Yeah, no presentation is complete without some code examples, so I will go through some real examples and code snippets to how we realize this one. But before jumping into the code, let's understand the motivation, why we need a distributed platform in the first place. So as a company, we want to utilize compute resources. We want to efficiently utilize compute resources. We should be able to justify the cost, why we need so much amount just for training or just for implementing this method. And we see that inadequate infrastructure leads to suboptimal modeling. Why? What are some of the examples? Let's say scaling. I want to scale, for example, some data scientists want to do a big data processing. He wants to do a large scale training. So he can easily get a 60 CPU machine or a 90 CPU machine. One VM, we get it. So what's the problem with that one? The problem with that one is it is underutilized. You may request for a 90 CPU machine, but when you actually do the training or maybe distributed computing, you may be using 60 CPUs. So basically 30 CPUs are unutilized. And so why cannot we horizontally scale? We cannot have more machines. That is an infrastructure problem. Scientists and researchers do not want to invest time in getting into those areas of like getting lots of machines and making a cluster and things like that. And also it happens that if you are stuck to one EC2 instance or one VM, you have to sample down your data frame to fit into a pandas data frame that runs on one machine. I cannot scale. And again, it's an infrastructure setup, pain to set up such a cluster. So as a user or as a model trainer or a developer, I do not want to get into that. So how can ML platform help? So our solution is Spark on Kubernetes. We started with Spark on Kubernetes, and I will briefly touch upon other technologies that Han mentioned. So basically in Spark, we have two methods, two ways of submitting Spark jobs. One is the client mode, and one is the cluster mode. In client mode, the Spark driver runs in your local machine or maybe on a VM, and then you submit the job to a host of executor nodes running remotely. In the cluster mode, driver and all executors run remotely. We submit the job there, and we just wait for the application to finish. So we leverage the client mode. Why we leverage the client mode? Because data scientists find they always work on Jupyter notebooks, and we treat the Jupyter notebook as the driver VM. And we spawn Spark sessions from the notebook itself and submit to a remote cluster. So this is a schematic architecture. It's very simplified, but it is much more complex underneath. In the center, we have something called LyftLearn Notebook. It's a Jupyter notebook hosted on a Docker image. And the notebook, and if you see on the left side of the diagram, you have like LyftLearn Spark image and ECR registry. What do they mean? That we have some base Spark images, those are stored in AWS ECR, and user can also use their custom images. So you do not have to stick to what we provide. You can bring your own Docker image. You can extend our Docker image to create your own, because you need your own different libraries onto that one. And we interact with the Kubernetes API server to request for executors when we build a Spark session. And that's how, and the executors communicate with the driver. We open a port in the Jupyter pod itself to interact with the executors and drivers. We also use Kubeflow TFJob and PyTorch on Horovod to do distributed deep learning. And I will not go into details today on that. But this slide shows that on the left side, we have a training data set, which is partition. And on the right side, we have a Kubernetes cluster with 6 GPUs. So what does it signify? It signifies that we bring Spark and Kubeflow at the same platform. So the first part, pre-processing, we are using Spark. The next part, we are leveraging Kubeflow's operators to train on those partition data. We pre-partition the data, and then we train each worker node on each of these partitions and then accumulate the gradients to have the model through using the all-ring reduced paradigm. We are also experimenting and actively experimenting with Ray. Just like I showed, we spawn a Spark cluster on the fly, asking the Kubernetes API. We also do that exactly same thing for Ray. Suppose we need a Ray cluster. We have constructs and SDKs that gives users a way to, from the Jupyter notebook, spawn a Ray cluster on the fly. So let's look at an example. Without looking at an example, this kind of theory is not complete. So here's an example. We have 2 cells here. In the first cell, what we want to do is, like, what does scaling mean in real life? I want to run a unit of computation in parallel. And the parallel can be, what is parallel? I parallelize based on some groups, some business keys, some other. Let's say I have a data frame. Lyft is operating in many regions. Region is a column. I want to parallelize per region. I want to do something per region. So scaling is that. So in here, first cell compute task, it takes a data frame, and then you do some extensive compute here, and you get a result. But how can I scale it? So that's a unit of work. One small data frame, that's a unit of work. How can I scale it? So we go to the next cell. So we see that we have Fugue transform, and then we have K8 Spark. There are two lines. The first one is with K8 Spark. I will come to that. And the second, third line is SDF create data frame and transform function. What do they mean? They mean that I can create a data frame. It can be a Spark, it can be Pandas, any data frame. But the main important thing is transform. I want to apply transform on SDF, Spark data frame. I want to apply the function compute task using the Spark engine. If I omit the Spark engine, it will be just Pandas. So what I'm doing is I'm applying a transform function, which is called compute task, on a bigger data frame, and the user does not even know that it's running on Spark. They just need to implement the compute task method, and that's all. And we abstract away all complications behind this magic K8 Spark. So if you see the construct K8 Spark cluster 444G, what does this mean? This means that I need 4 executors, each having 4 CPUs, and each executor having 4 GB. That's all. That's it, done. And you apply the function on parallel on my data frame. I can unit test it. I do not need, for example, when I'm just trying out things, I do not know whether I'll be able to scale in Spark. I just need to unit test it, no problem. Write the compute test, create a Pandas data frame, create a small data frame, apply compute test, make sure it works. Make a even larger, a little bit more larger data frame, apply compute test, make sure that unit test works. If everything goes fine, then you come to Spark. So we try to make the most common thing simple, less code, and don't worry about the infrastructure. So, but is K8 Spark enough? Just I create, how does the cluster create? That is enough? Just creating some nodes and it's done? No. The reason is we may need some volumes or EFS volumes to get mounted on the executor's node. The user may be writing something on a shared storage. How does that happen? The user may be needing to access S3. How does the credentials get in? The users maybe need to assume some special roles to access Kinesis streams or access S3 buckets or access other things. How does that work? Every such thing is hidden inside K8 Spark. So users do not need to worry at all. Just focus on your business logic compute task. We will take care of the rest. And you just apply the transform function using Spark. And also, if you see the method compute task, it has some annotations, schema star result string. What does this mean? It shows that, okay, my output column would be a string, and Fugue transform reads these annotations and transforms the data frame input and output accordingly. So this was a compute example. Let's say another example, prediction. I want to do distributed predictions. Why it is distributed? I have a data frame which has, like, let's say a business key called region, and I also have a model per region. I want to predict per region, but I also want to scale it. I want to scale it to San Francisco, Los Angeles, New York, and I have regions accumulating, but I want to spawn a job for each of them. We follow the same principle here. The first cell shows a method called predict, and it assumes that I get a partition of the data frame because we partition by some key. Let's say that is that partition. Region is being the key. And we load a model and then we do prediction. Once we write that small unit of predict function, we can unit test. We can use a Pandas data frame, just have one region, San Francisco, test it. It works or not. If it works, scale it up, go to the second cell. We get all region data from S3 location, apply the same principle that I discussed in the last slide. Transform all region data using predict. The only difference here is there is a new keyword called partition. We are saying that I have a bigger data frame. I want this logic to be applied. I want it to scale up based on this business key by region, and then finally write the output. So here you see, again, we're focusing on making your task simple. It's not no code or low code. You just focus on your business logic. As a platform, we will take care of the rest. Partitioning, dividing, scaling up, and bringing up and down the cluster, and things like that. So we talked about Spark, we talked about Ray. Can they both work together? The answer is yes. Since everything is SDK based, so let's look at this example. So there are 4 cells after the import statement. And what is a typical process of a machine learning workflow? Usually there is 4. We do some pre-processing, feature engineering, train the model, save it and load it, post-process, predict, or do some other data processing. So there are 4 cells. The first one, we use a Spark cluster to read the raw data and do feature engineer and write it. The next part, we want to train a LightGBM model. We want to use Ray's LightGBM distributed LightGBM support. Can we do that? Yes. Instead of with K8s Spark, call K8s Ray and supply the same construct, cluster. And then call train LGBM remote, that I want this method to run on remote clusters, and then Ray get the output from those remote clusters in a machine. And then we save the model, and then in the post-process, we load the test data, we save the model in third cell, just load that model and do, again, call transform to predict using that model on that test data. So we are actively working with the Ray team for that, and Anthony helped us a lot to get it in a working shape. Anthony from Ray team. So you see the entire workflow is on this single slide, and it is on a single Jupyter notebook. And every cell has a different cluster configuration. I need bigger clusters for data processing. I need smaller clusters for LightGBM Ray. And every cluster size is different. As per the job I need, I tune my cluster size. And the code which is running actually, these 4 cells, it's a Jupyter notebook. It does not need to be a powerful machine at all. It can be a simple 4 CPU, 8 GB machine. What it needs is just to orchestrate, and everything is taken care of in the background. Okay, so when we build such a system, it is bound to have some problems, some learning, some challenges. I will highlight a few of them. So what we found that having a standalone cluster was not a good solution for us, because most of the time it runs idle. And our data science experiments are mostly bursty. Like they will query the data, do some compute, but then they will spend some time in exploring, visualizing, things like that. We do not need cluster for that. And they want custom Docker images. So Spark on Kubernetes just gelled well. So our platform is entirely on Kubernetes, and we want to have the strong support from Spark, so we could distribute the compute. At the same time, we can customize Spark Docker images. Users can use their own images. We do not tie them with our provided images. And since Kubernetes, as you all know, works on the images are cached, so spawning up Spark pods is very super fast. And the beauty of this is Spark scheduler and Kubernetes scheduler work in tandem. So what does that mean? That if there are fragmented resources scattered in the cluster, for example, I need a 4 CPU executor. Let's say there is a node, maybe there are 64 CPUs, 60 CPUs got consumed, something else is running on. 4 CPUs are hanging around. So these schedulers work in tandem to grab those 4 CPUs and give an executor back to us. So what's the result? We can get optimized resource allocation without increasing the number of EC2 instances on the auto-scaling group. So all resources are being scavenged and used and reused. And also so there are 4 benefits. Custom Docker images, You can image caching, and the EC2 instances are not are reused, and it's very fast. And we have this platform is extremely well received in the company, and there are statistics, and we frequently hear, okay, my job was running for 2 hours, now it's 20 minutes. It was running for 8 hours, now it's 1 hour. And we have got great feedbacks on this one. The problem with more usage, we land up in another problem. It's a real problem. Like the other problem is a happy problem. Like we are using so much, but I want to keep the cost low. I don't want to let users throw away rampant clusters. They should not be spawning clusters. There should be some check. As the management sees why that team is spending so much, is it justified? How can we do that? How can I track those problems? The trick we applied is you have namespaces. Users cannot spawn Spark cluster beyond your own namespace. And we apply, again, we leverage Kubernetes constructs, like we apply pods, annotations, and labels. Custom pods, annotations, and label, like this pod is spawned by ML platform, this team, this user. Why do we do that? Because we use an event listener to listen to those pods and events, trap it, and record all pod starts, pod completion events in a Hive database. So we can analyze later using Hive queries that tracking those pod UUIDs. This pod UUID started at X and it ended at Y by this user who belongs to this team, so that we can have a billing dashboard like this. We do cost cutting like here. And we have a regular report, like your team is spending like $4,000, it is justified for last 7 days. And you can see on the right side, there is a chart, Spark job, that is consuming almost like 40% of the cost. And on the left side, there is a chart like per team. I have deliberately masked the team's name, but that's the way we do it. And the other thing is, if you have seen here in the last cell with K8s Spark, everything is embedded inside that context manager. What does this do? This helps to keep check on the Spark session. The Spark session is created and gracefully shut down and terminated as the code comes out of this cell. So you cannot have a orphan Spark session running and executors running. We do not let users do that. They will always be terminated and killed. So that saves us from orphan nodes. And I will end with a real use case, a real problem we faced. A user, when we are just implemented this system, a user created a for loop, and it ran 100 times, and inside each 100 times, this spawned a Spark cluster. So there were like hundreds clusters spawning by one given user, and it just bombarded our K8s API. And not only that crashed that user's namespace, the etcd server, which is the database for K8s, that came down, although that had 3 replicas. And all other users, all the other namespaces, they could not spawn a job. We are getting DDoS attacks, denial of services. They could not do it. We could not track it. We took help from infra team finally to crack that etcd was the problem, because the etcd were recovering intermittently. So some users were able to run some Spark executors, some were able to not run, and this was like a very complicated scenario to debug. So how did we tackle that? Again, K8s comes to rescue. We have Kubernetes resource quota. We now say per namespace, a user is allowed to only spawn 2048 CPUs, 2048 CPUs with 8 terabytes of memory. That's the default. Are you a special user? Yes, we will provision special for you. You are allowed to use 16 terabytes and 4,000 CPUs, but you have to do through runtime configuration and go by us to justify your use cases. And we also have like other job controllers. For example, sometimes we miss some Spark pods or fans. Those job controllers, again, scan the custom annotations and labels to kill those pods. So we end there, and we'll take questions now. There are some engineering blogs and some talks on Fugue coming up. And if you are interested in contributing and working with us, please feel free to connect with us. We are happy to talk in more details about the implementation. Thank you, everyone.